That back again for you to stare at. So the question is, what's going on here? Something is moving to the right. It's what you're probably thinking. But your eyes are deceiving you. Yeah, have a look at the red one in the middle. The little red dot. Yeah, that's well put. There's a little red dot in the middle.
Okay, yes. Red dot.
And the red dot isn't moving.
Okay.
It's just going up and down.
Up and down.
Yeah. Well, it's moving, but it's not moving to the right. That's so in fact, all of those dots are doing what the red dots do. They're all just moving up and down. But what we're seeing something. Actually, it was that is to my 16-year-old daughter, and just without the red dot, and she said, "Oh, why don't you color one of the red to make it to see that it's actually going up and down." Okay, so I don't know if I should start on time. In our university, we always start 5 minutes after the hour. Give a couple of minutes for people to come. But while we're waiting for anyone else to arrive, I'll just say thank you to the organisers. It's been a really great program so far. Yeah, it's good to be here. I'm sad to be going back after this week that we're going teaching months. Maybe I'll try and pop back occasionally.
Maybe we start on time.
Yeah, should we start on time? It's up to you. I'm happy to start. We've got the room for a little bit longer. But I don't want to keep the room.
Gerald, can you just present the speaker? No, it's just because being important.
Yeah, I can present myself.
Present yourself.
Yeah, my name's Sandy Hone. I'm from the University of Kent, and I'm going to talk about continued fractions, hyperelliptic curves, and orthogonal polynomials. Okay, thank you. So the video, the little movie that I'm showing at the moment, is an animation of a solution of the infinite Toda lattice. So in these Blaschke variables, Vn and Dn, what I've plotted actually is just Dn as a function of t on 200 lattice sites. And this is an exact solution that's given in terms of elliptic functions. And it comes from what I'm going to explain today is how it naturally comes about from the continued fraction expansion of a function on an elliptic curve, and then show you how actually this generalizes to a whole class of solutions of the Toda lattice in terms of continued fraction of hyperelliptic functions.
Sorry, Andy, I saw other little circles or diamonds, locations.
Yeah, these are so what this is, the horizontal axis is n, which here goes from 0 to 200, and then what's being plotted is dn of t, or n going from 0 to 200. So that's what this solution looks like.
What do the little diamonds indicate?
The value. So if we freeze it for one instant of time, then that gives you at lattice site 100, say the red dot, then that gives you the value of d100 at time t at that time. And then this is the motion. So the motion of each particle is the value at each lattice side is moving up and down with time, in this case in a bounded domain. So it's up and down. Yeah, so that's what you're seeing. And if you can do the same plot for the other, these are normally called the Flaschke variables up to some square roots. So you can also do the same plot for Vn, and the picture will be very similar, except that it is between some slightly different values.
Sorry, what initial conditions are you using?
I can tell you what the initial conditions are. The initial conditions are given by well, okay. So it's best if I explain how the initial conditions come about. So in fact, in this case, what we need to do is, in fact, for this to generate this solution, we prescribe the value, say V0 and D0, and then there's in fact a symplectic map which iterates in n and gives you the initial conditions for all the other lattice sites and for all integers, and then these things also can be evolved in time. So in a sense, this comes from a two-dimensional system, and then it evolves in time. And the kind of solutions that you can get from the construction that I'll explain come from a 2G dimensional set of initial conditions. But there are also other parameters. So at some point I'll try and explain the exact initial conditions, why I chose these initial conditions. Yeah. Okay. So how do these things come about? Just sort of background for some models that some people in this audience might be interested in. In random matrix models, you have a partition function which is given by which takes form where this is an integral over n by n Milton matrices, and this is given by the trace of some potential evaluated on M, where M is a function with suitable growth conditions at infinity. And what one normally does is starts with something which is n. So typically you start with a Gaussian and then powers of m. And there are various things one can do, but one thing is that already you can simplify this by integrating out the sort of angular degrees of freedom and end up with just an integral over the eigenvalues of n, and then you end up with basically a van der Waals factor and just integrating each to the minus v lambda j, so over the n eigenvalues up to some proportionality constant. And so what people are often interested in is actually the large n limit. So there's some error. Various kind of let's say limits, but where you take n goes to infinity and you tune the parameters appropriately. So there's at least two. I mean, if we, for example, we might just have two parameters here, or just one parameter here, and then we take n to infinity, and we also take the coupling constant, the one single coupling constant to a certain value. And what this gives you is what this corresponds to is particular solutions of Painleve equation. For example, Painleve 1, Painleve 2, sometimes solutions of Painleve 4, various different Painleve equations or higher order Painleve equations arise from this double scaling limits of matrix model. But in fact, even without taking without taking any limits, before you take the limits, you can write Zn, this partition function, in terms of orthogonal polynomials with this function being the weight function of the orthogonal polynomials, and then you can even show that you get solutions of the Toda lattice, where or in a slightly more restricted case, the Volterra lattice, where now n, n actually corresponds to this index n that I've used here, but on the half line, because and you can explicitly write formulae, but it's not sort of any old solution. It's also the solutions that you're interested in that satisfy what's called the discrete string equation. So in the continuum limit or the scaling limit, you get the string equation gives you Painleve 1, Painleve 2, or some Painleve equation, but without taking any limit, you already get a discrete. You already get a discrete Painleve equation, which is the string equation.
Just for clarity,
Yeah.
clarify that the lambda in the potential parameter is different from that.
Oh, I'm sorry. Yeah, that was probably maybe actually because I'm about to
Yeah, just for
because I'm about to you do say this anyway. There's that. Yeah, thank you, Antonio. There's this. I sort of got obsessed with thinking of lambda as coupling constants, and then I also use it to mean argument. But yes, in fact, there's in case anybody was, I'm sorry if anyone was confused, these lambdas are meant to be the eigenvalues of n, and they have nothing to do with these parameters that appear here. Thank you. Right, so for example, so if we have, so in fact, this is relevant to, well, Antonio's is an expert in this, but so in fact, the in this setting, before we so that now just to clarify exactly that point, that the coupling constants Tj become times in the Toda lattice hierarchy, and a special case which Antonio Moro and his collaborators have considered recently. A special case is where you only have even times. So T2j, you set all the odd times to 0, and then you get orthogonal polynomials, let's say un of x, with a 3-term recurrence. So let's say qn plus 2 x qn plus 1, and maybe don't get up to possibly shifting the index on beta. And the recurrence coefficients in this case beta n satisfy the Volterra lattice equation with respect to the time t2, so the time that appears in front of the quadratic term, and that the Volterra lattice is this equation. Okay, so, but this will be for n greater than or equal to 1, so on the half line. Okay, so the picture that I started off with is a Toda lattice on the infinite line, and if you like, part of the moral of my story is that you can construct these solutions of the infinite Toda lattice from hyperelliptic curves, and there you get now in the system that I just rubbed out, the Vn and the Dn will appear as the Vn will appear with the sorry, capital X will appear with the X term, will be X plus Vn, and the Dn will appear here as the constant. So that's the story I'm going to get to, but that was sort of just to motivate you and maybe connect it to things that some of the audience are specifically interested in. But now I'm going to completely change gear and talk about continued fractions, and then eventually you'll see how continued fractions are related to this story. If you don't know already. Okay. Okay. So continued fractions in R, in case you didn't learn this at school, and I didn't learn it at school, so it's something that I learned sort of in later life. So to calculate a continued fraction, a regular continued fraction expansion of a real number, you take the integer part, and then the remainder is a number between 0 and 1, and you take the reciprocal of that, and that gives you, take the integer part of that gives you another number, and then you keep on taking remainders and reciprocals and taking the integer part, and you can go on. And if I didn't make a mistake, it's possible that I put too many ones, but what happens with this fraction, the square root of 7, is that this pattern 1, 1, 1, 4 will now keep repeating forever. So this is, you could say it's pre-periodic or eventually periodic, and it's a well-known classical result that the continued fraction in R is eventually periodic. Obviously, I mean, this process will terminate if you start with a rational number, but otherwise it will be an infinite fraction, and it will be eventually periodic if and only if the number is a quadratic irrational number. Quadratic irrationality. So the sort of simplest example you probably know is the golden mean, where it just goes 1 plus 1 plus 1 plus 1 over 1 plus 1 over 1, and so on. Now, and then of course there's also the convergence of this fraction. So the convergence are what were they? 2, 3, 5 over 2, 8 over 3, something. I did write some down. So, oh yeah, 37 over 14. That was the last one. I stopped. These numbers, sort of Pn over Qn, they each satisfy the same three-term recurrence relation. With these numbers, let's call this A1, what we can call this A0, A1, A2, A3, A4. So they satisfy a three-term recurrence, like Pn plus 2 is An Pn plus 1 minus Pn, and the same thing for Q, where those partial quotients or coefficients A, the Ans, those are the coefficients of the Pn. So if I didn't make a mistake, you can check that those rational numbers are generated. Now, what about if we go to a function field case? Well, that was considered classically, but not completely understood. So let me say what I mean. So if we take Laurent series, so that means we have a tail of positive powers and then an infinite series. So Laurent series in 1 over x. So, well, here's a nice example, and this is a baby example of what's going to be in the rest of my talk. So this is actually the genus 0 version. So here's if we expand where we take the root which looks like plus x, then that's what we get. And the convergence, okay, well, I'll leave a question mark there for a minute. So Arbel and Chebyshev thought about the continued fraction of the square root of a polynomial, of an even degree polynomial, but they only obtain some partial results on when you actually get a periodic fraction. So I'll come back to that in a minute. But just for this cute example, the convergents are x squared minus 1 over x, x cubed minus 2x over x squared minus 1. And what are these things? Well, these are actually Chebyshev polynomials of the second kind. So you get the three-term recurrence relation here. This one. That's easy to check. So the idea is that we're going to we're doing the same, essentially exact analog of the algorithm in R in the following sense. But given a power series, a Laurent series like this, we instead of integer part, we take the polynomial part, and then we have a power series in negative powers of x, and then we take the reciprocal and take the polynomial part and keep on doing. So that's the algorithm in this field of power series. So it works in the same way. I mean, yeah, all the formulae look formally the same. But in fact, the result on periodicity, well, the best result is actually only from 2016. Umberto Zanier says that so it's not an if and only if statement, but if you take a square root of an even degree polynomial, then you find that the sequence of degrees of the partial quotients, these coefficients that are bit, then that is eventually periodic. And his methods, I mean, he kind of says, if you took a combination of a square root plus some other rational function, then the same result should still be true, but he doesn't try to work out the details in a slightly more general case. But his argument is based very heavily on the algebraic curve, which is defined by y squared equals p of x, which is a hyperelliptic curve in general. And so he uses really the geometry of the curve to prove things about these continued fractions. Okay, so that's my setup, and that's what I want to do. And why do I want to do? Why do I want to do it? Or why did I want to think about this problem? Well, it didn't come from thinking about Toda lattices or about continued fractions, but this is the point that Alfredo was waiting for. That nearly every talk I have to mention Sommer sequences. So Sommer sequences are sequences defined by quadratic recurrence relations, and they appear in many contexts. So in the beta ansatz for the hard hexagon model, and dimer models, and counting VPS states in more recent times. But the simplest example of a non-trivial example of a Sommer sequence is the original one, which was found by Michael Somos, who was a computer scientist. And what he observed is that if you take this quadratic recurrence relation and you take the four initial values to be 1, then, well, every time you iterate here, you have to divide by tau n. So the first 4 times you divide, you're dividing by 1 and nothing special is happening. But when you next divide, you have to divide by 2, and you finally get an even number. And the next time you have to divide by 3, you get a multiple of 3. And then you divide by 7 and 23 and 59. And anyway, the surprising thing is that you get, at least what he saw, first of all, empirically is that you get an integer sequence. And then various proofs came along, and perhaps the most useful observation, which sort of generalizes this, is that actually this recurrence relation has what's called the Laurent property. And this means that actually the iterates are Laurent polynomials in the 4 initial values with integer coefficient. And so clearly, if we substitute all of them to be 1, then we get integers. And you can sort of try and prove this directly by induction. It's not actually that much harder than trying to prove it for this specific sequence by induction. If you need an extra assumption about coprimality of 4 adjacent terms, then it works. And you do the same thing in the ring of Laurent polynomials, and you can prove that this has the Laurent property. But actually, a sort of nicer way perhaps to understand this is that the sequence lives in a cluster algebra. So I'm not going to give you a full talk about cluster algebras, but Bowman-Zelewitzky's theory of cluster algebras includes this as a particular sequence of mutations, and the Laurent property is something that's built in that comes out of the axioms of a cluster algebra. So in fact, this allows you to generalize it to well, lots of other examples where, at least if you have a sum of 2 monomials on the right hand side, and if it's a quadratic recurrence, then in fact that actually means that it can be obtained as a reduction of the discrete Hirota equation. So which is like the discrete KP, the bilinear form of the discrete KP equation. So there's another way to understand these things in terms of, if you like, plane wave solutions of the discrete KP equation. So there's also integrability here as well as the Laurent property. Yeah.
Does that extend beyond quadratic?
Well, this property, yes. I mean, in cluster algebras, you could put. Well, I can give you like exact conditions, like so any order and some conditions on the exponents, but they can be any degree. Yeah. But the connection with integrability is very specific to quadratic, so that's very limited. And then also, if you want to add more terms, there's something slightly more general called LP algebras, which are either Laurent phenomenon or Laman-Piasky, who are the people that introduced them. So you can sometimes also extend to more terms, but somehow, but in general, well, if you keep quadratic, then if you have more than 3 terms on the right hand side, then it destroys the Laurent property. So and that can be sort of understood from, if you like, from the point of view of integrability, that if there are 2 terms, then it corresponds to KP, and if there are 3 terms, it corresponds to BKP. So the Miwa equation. Okay, so yeah.
Going to be a cluster algebra, even if you have more than quadratic, shouldn't you be able to reduce it to a quadratic but in more variables? No, in general, no. No, I mean, for example, a very simple example, in second order, if I have cluster rank 2 cluster algebra, then this recurrence, let's say, I don't know, b plus 1. So any positive integer b will generate a rank 2 cluster algebra. You can't reduce. Yeah. So this also has the Laurent property. It comes from. So I mean, these ones are all defined by quivers. So you can just put b arrows between 2 nodes, and that's the quiver that defines this cluster algebra. Yeah. Okay. So I studied these things a long time ago. Originally, they were introduced to me by a number of theorists, because they include things called elliptic divisibility sequences, which are the kind of genus 1 analogues of like Fibonacci sequences or Lucas sequences in sort of linear recurrence relations. So there are some particular types of these recurrences which will give you divisibility sequences. I understood, I mean, really from the connection with integrable systems, how to find the analytic solution of this recurrence in terms of the, I mean, to solve the initial value problem in terms of, you can solve it with the Weierstrass sigma function very conveniently, or if you prefer, you can use the Jacobi theta function. So essentially, power is given by a theta function, and but at the same time, or almost at the same time, Van der Poorten was thinking about these things, and he found a way to construct these sequences from continued fractions, and then he was trying to generalize it to higher genus, but he only had some partial success. So I guess my sort of goal then was to try and understand what Van der Poorten's construction meant, and then actually to make sense of the higher genus case. So
Is that Alf Van der Poorten?
yeah, that's Alf Van der Poorten. Yeah,
Australia.
Australian, Dutch Australian. Yeah. So the idea is you take a hyperelliptic curve of G given by an even model. So this is kind of well, I call it P of X there, but let's say F of X. So the degree is 2G plus 2. So if F doesn't have any repeated roots, then this defines a smooth curve of genus G. And then we want to take a function, a meromorphic function on this curve. And we don't take any old function, we take a function with a very specific form. So I'll call the function y0, and it's given by y plus, let's say, p0 of x divided by q0. And okay, and then well, just to say some more conditions. So the degree of p0 is p plus 1, the degree of q0 is g, and then to make life simpler, we also do some normalization. So we can complete the square in F. So we write F is a of x squared plus 1 r of x. And we're going to take is going to be monic, and then we can always shift x if we like to get rid of the term here at order g. So this will be something of order g to the -1, but otherwise arbitrary. And then also we're going to take p0 to be a of x. So the first part of p0 is just given by this g plus 1 degree polynomial a, and then I'll write it as 2 0 x to the g plus plus lower order terms. Okay. And U0, I'm going to write it as U0 x to the g. I'm being rather specific about the how I denote the coefficients for the region that we'll see in a minute. Okay, so that's our starting point. I'm going to stick it up at the top. Oops. Okay, so now we're going to apply this continued fraction machine. And actually there's one more condition that I mentioned. So we also assume that Q0 divides f minus P0 squared. So that means there exists some polynomial Q minus 1 such that f equals P0 squared plus P0 Q minus 1. And this might seem a bit obscure, but we'll get the idea in a minute. Okay, so then we apply, we think of this as a Laurent. Yes?
You already composed it in that form. Do you do it again?
No, I mean, I'm saying it's a further assumption.
It's not the A is not the same.
No. I mean, I'm assuming. So let's say I'm given this P0 and A, and I have a Q0 of this certain form, and I have a further condition, which is that that Q0 should divide this. Yeah. Okay. So for the construction to work in the right way. So this is what this leads to a property of the continued fraction, which Vanhaecke calls reduced. But it has a very important consequence. Okay, so now we do the continued fraction, and so we get we can write it like this. And we'll keep on doing it. So this is just the same notation. So this is just for the standard notation for continued fractions. And the point is that because of the way that I've set things up, then degree of A0 is 1. So in fact, A0, in terms of, if you do the calculation, then A0 is 2x plus V0 divided by U0. And then because we've set it up in this way, and all subsequent AN of this are degree 1. Okay, so this gives you an example of what's called a J fraction, or classically it's a Jacobi continued fraction. So then what we get by this iteration, we get a sequence of functions of the same type. So everywhere where you had an index 0 in my initial polynomials, you can replace that by an n. And so each line of the continued fraction will give you this recurrence. So like yn is an, which is a linear polynomial, plus 1 over yn plus 1. And but there's more. What we also what we also find from the assumptions that we made about this divisibility property are that we can write, we've started off with written like this, but then also we can find a sequence of, with this sequence of q's, we can also write this as qn minus 1 of x divided by y minus pn of x. So this is a consistent recursion that comes from the initial assumptions, but we have, in fact, the same condition for each n. And for people who work in integrable systems, they will recognize this as this defines a spectral curve from a lattice pair. So let me then explain how that works. So what we do is to see how we get a discrete lattice pair is we take yn to be a ratio of projective coordinates, and then we can separate out these two equations. So and let's take psi n to be the vector made from these two projective coordinates, and then what we get is two equations. So an eigenvalue problem for this wave function psi. So that comes from this equation, from separating out this equation, and a recursion equation also for psi, which takes this form. Okay, and if you're so what are the matrices? Well, L is the matrix which is the closest matrix which has Pn minus P on the diagonal, and it has Qn minus 1 Qn from the off diagonal, and Mn is a familiar matrix from the theory of continued fractions. If you're used to using ordinary linear fractions, you'll be used to constructing continuance from this matrix. So this is a pair of linear equations for the vector psi, and of course it has a linear system and a compatibility condition, and the compatibility condition is what's called the discrete lattice equation. The lattice equation, if I get it the right way around, should be it should be this way around, and then ln plus 1 plus ln mn. So what this tells you is that the spectrum, this is an isospectral evolution, that the eigenvalues of L are independent of n, or a better way of saying this is that the determinant of L, the characteristic polynomial of L is independent of n. But that's sort of built into the thing, because that's the curve C that we started with. So often in integral systems, you sort of go the other way. You have some system, and then you look for a lattice pair, and then you find a spectral curve. And here it's sort of like we started from the spectral curve and a function, and we get this system. So what does this give you? Well, I don't want to go into all of the details, but I don't have time to do that. But what we get is a dynamical. So we get a dynamical system in dimension 2G, which is for the coefficients of, so if we want to be a bit more careful, we should take f minus we should take a of x minus Pn of x, and there's a sort of pesky normalization factor which I've rubbed out, but actually the top coefficient of Qn, it doesn't play any role in it, we can eliminate it. So if you do the counting right, and I'm not going to try and do it just now, but you'll find that you get so essentially this rule for the top equation, if you write it in terms of the formula for y in terms of Pn and Qn, it gives you recurrence relation for Pn and Qn. And that gives you a dynamical system on the coefficients, and if you count the coordinates right, then it's in dimension 2G. And then but I'm going to sort of skip those details a bit and just say the map for coefficients of Pn and Qn is a symplectic map in dimension 2G with G independent and so quantities so let's say H1 up to HG, which are in involution. So there's a Poisson bracket associated with the symplectic structure. So these function Poisson commute. So what does that mean? That this is a discrete integral system in the Liouville sense. So this is what we call Liouville integrability. Okay, so maybe a good time for a little break is if I just show you a little picture.
Is there any notion in which Hamiltonians generate this shift?
Yeah, it's possible. It is possible to do something like that. So you can look at you can define a generating function for the map if you which will be sort of in a way formed from compositions of these like exponentiating Hamiltonian combination of Hamiltonian vector fields. Yeah, so that's the sense in which it is. But it sort of kind of moves in all of the directions at once. It's I mean, a combination. So it moves in a suitable combination of all the directions. And there's a very nice way to understand it geometrically. So hold on, let's go to share screen again. Yeah. You're not seeing it yet.
No, it's not the board.
No, I know I do. I'm just trying to see if I can get the thing here on my screen before I should try and show it to you. That's all. Yeah, so I need to move this down. So I don't know. Let's move down anymore. Yeah, there we are. This is the genus 2 map. So it's a map in 4 dimensions, but I've projected it into 3D by just projecting down to 3 coordinates. And you can see a nice Liouville torus, two torus, which is the level set of the map. But also, from a geometrical point of view, you can actually think of this real torus as being sitting inside an open part of the Jacobian of the curve. So that's a 2-dimensional complex torus. And the way that you can get that is essentially by sort of separating variables or spectral Darboux coordinates. Because if you have a look at this function yn at each line, or that you have, the divisor of poles of this function is okay, I'm sorry, I missed the sort of, if you want to think about this correctly, this curve has 2 points at infinity, let's say infinity 1 and infinity 2, which corresponds to the choice of square root you take. So whether it goes like plus x to the g plus 1 or minus x to the g plus 1. So what we're doing really is expanding this function on the curve around infinity 1, where we take the plus, if you like, the plus root. And so the divisor of poles of this function is degree g plus 1, and it consists of the point infinity 1 and the points correspond to g roots of this polynomial of degree g, and the divisor of zeros corresponds to the g roots here in the numerator plus infinity 2. So this function it vanishes at the other point at infinity. So so now these two divisors are linearly equivalent. So you can see that the point on the Jacobian is represented by the divisor of g points, and here you've done a shift by the difference of infinity 2 minus infinity 1. So all you're doing is translating by this fixed vector on the Jacobian. Each iteration, each line of the continued fraction is a shift by this fixed vector on the Jacobian. So, so that's what you get. So now, I guess the last part is just to explain where the orthogonal polynomials come into this story. Well, just like in the case of matrix models, we have the I'll stay on this thought, sorry. In the case of matrix models, we had the weight function, which was defined by this the potential appearing in the matrix integral. Well, here it's a little bit different. So, and I'll try and so I believe that in certain cases, at least when the curve is real and has some symmetry, so let's say it has real roots, then you can turn this into a set of, you can get a set of orthogonal polynomials with measures supported on G intervals, which is also something which naturally appears in different scaling limits of matrix models. But the way to actually go about it is to define, let's say little phi. So take any function, and we can define a linear functional by integrating around infinity against a certain function. This is going to be around the point infinity 1. And what is G? Well, y0 minus a0 is a function G, which has an expansion, is a moment generating function. So sum j naught of sj x to the minus j plus 1. So this is the tail, if you like, in the function that we started with. And this gives us a linear functional for suitable functions on the curve, if you like. And the powers of, if you integrate powers of x, then these sj are precisely the moments of this functional. And then you can define, well, this, as we said, this is a Jacobi continued fraction, and its expansion looks like, I think if I put my normalization correct, there's a sort of initial normalization, and then we expand like this. Okay. So this is a J fraction. This is a Jacobi fraction. At least when we start from the negative powers of x, and we get we have a Faraday approximation problem for this function g, where we get a sequence of polynomials Pn and Qn, which are the convergence of this fraction, and we have Gn minus Pn of x over Qn of x. These are the convergence. Into order x to the minus n plus 1, and then the standard orthogonal polynomials yoga then tells you that you have a three-term recurrence relation for these polynomials, which is, I wrote all my indices in the right place. Then it looks like the at least the denominators were u0 1 and u1 is x plus v1, and this works for n. This is for n greater or equal to 2. And then and these things are orthogonal with respect to this. You take the product with respect to this functional, you get ratios of Hankel determinants, which are given by the moments. So Hankel determinants, so delta 0 is 1, and delta n is the n by n determinant. And then we also need some ordered Hankel determinants, which are given by also determinants of size n, but where we miss out a column here. So sorry, yes, Sn, and then well, so we take the sum Hankel, if you like, and then this is S2n. If you make a mistake. So this is like a ordered Hankel or gifted Hankel. And then there are standard formulae from orthogonal polynomials, which then tell you that you can compute the coefficients here, the recurrence coefficients, in terms of the Hankel determinant. So this was interesting for me, because in terms of the Somos sequence, various people had conjectured and then partially proved some results on Hankel determinant formulae for Somos sequences, but they had to use very complicated sort of generating functions and determinantal identities. But the point is that if you use these Hankel formulae, which are also kind of standard in the Toda, then actually, and then okay, so then I would just say sort of nice corollary, for example, is that in G equals 1, you get Somos 4 for the sequence of Hankel determinants delta n, and it's well, in general it's Somos 4 with the general Somos 4, which has a couple of free coefficients you can choose in front of the right hand side of one. So one squared, 2 squared, sorry. So you asked me about the initial conditions that I did in my Toda lattice at the beginning, they were exactly chosen from taking that sum of four sequence that I wrote at the beginning, where you start with ones, and then that gives you a sequence of dn's and vn's. So everything that I've said so far is about, more or less, is about maps, apart from your question about vector fields. So the point is that also these Hamiltonians, H1, H2, and so on, generate Hamiltonian flows. And the point is that if you also combine the H1 flow, so the flow of the first, as a sort of natural ordering of the Hamiltonians, then the first flow, Hamiltonian flow, combined with the iteration of the map, gives you solutions of the infinite Toda lattice. So that's how you get it.
Can I ask you something?
Yes, yeah, of course, yeah.
How you know you can integrate that? You have to somehow take a contour that.
Yeah, sorry. You take a small contour around infinity, and let's say, well, so certainly if I guess what I'm interested in is when phi is a polynomial, and certainly when phi.
Still, sometimes you have to like a limiting.
Well, no, in this case, I mean, this is really a convergent series for the function around infinity. This is just a convergent, and so just if you take the moments, I mean the power, then it's fine. But if you took another function, then I agree that there could be poles, yeah. But just around infinity, this function is this is a meromorphic function in the neighborhood of infinity, and you can multiply it by a polynomial, which is another meromorphic function, and then compute the residue. So it's perfectly well defined, at least for the polynomials of x, which is all I need here to prove orthogonality of these polynomials. Yeah, is that you? I mean, we have a product of meromorphic functions defined in the neighborhood of a point, so we can just compute the residue. That's just Cauchy's residue theorem. So there are, of course, if we did take other functions with poles somewhere else, we took a larger neighborhood, then poles can appear. But in fact, what I was kind of alluding to is that the baby example that I put right at the beginning, which was the Chebyshev. So if you take the integral, so there you have square root of x squared minus 4, which defines your genus zero curve, and if you move the contour, there are no poles in the function that I took. There are no poles if you take the top sheet, if you like. So you take branch cuts between -2 and 2. There are no poles anywhere else. So you just move this contour around, and then what you get is an integral around here. But then also by symmetry, you can turn this into an integral just on the top of the cup, and that gives you the standard weight for the Chebyshev polynomials of the second kind, right? So now if you do the higher genus version, well, then it's a little bit more complicated, because if you want to move this contour, well, the function g does have some poles elsewhere in the plane. So I guess what I need to check, which I haven't checked, is if all the poles are just in the same sheet, then you know the sum of residues of a meromorphic function on a Riemann surface is 0 on a compact Riemann surface. So the contribution from the poles, I could be completely wrong, but I'm guessing that if the poles are in the right place, then you get 0 contribution from the poles. And then what you end up with, so for example, in genus 2, you will have an integral around 2 intervals, because you can deform it onto 2 cuts, and then again by symmetry, if you have real roots. And again, to maybe come back to pictures, to finish with another picture. Already run over an hour, so let me just show you, finish with one picture. So the polynomials, the polynomials in genus 2, I computed some polynomials in genus 2 which have where the sextic has 6 real roots, and this is the 90th polynomial, And what you can see is that the zeros of the polynomial, well, you can see that they concentrate on two intervals here, but then if you actually blow up the picture, then you can see that also there's a middle part which you can't see from the scale, but there's also a third interval in the middle, and it looks like the zeros are sorry, have I gone? Yeah, it's down.
Can you bring the image?
There we are. Sorry. So what I showed above was zooming out, and you can see two intervals, but there's another interval in the middle where the values are much smaller, but you can see that the zeros are also concentrating on the middle. And there are results about this equilibrium measure of zeros of polynomials. So this seems to be consistent with what you would expect. I'm not so much of an expert. I think some of you are more expert on this property of polynomials. Pictures. I said the pictures don't lie. They can lie, but anyway, the pictures suggest that this is correct.
But you have examples where the measure for planarity gets.
Yeah, well, what's interesting, so I mean, I think there's a sort of even actually Chebyshev's student Duma considered elliptic polynomials, and there are cases. So if the roots are, I think if the roots are complex, for example, then the zeros of the polynomials can wander everywhere in the complex plane, and so.
In the real case, I mean, because in your picture that you brought before,
Yes.
You were sort of breaking apart the branch sometimes. Right?
Yeah.
In that case, you have planarity in separate intervals.
I think what I believe is that from the way that I've defined this, the product should be the measure is supported on all three intervals. That's what I to define the orthogonality. You need to integrate across all three intervals in this case. Yeah. Because
the zero complex doesn't the measure become complex?
Yeah. I mean, of course, it becomes complex value. Yeah. I mean, you can think about this more generally of having a complex measure and so on. It's certainly so. In that case, I would say that this is sort of maybe the only sensible way to define it, because if you try to move around, you don't find that it looks like. Well, I mean, there are some theorems. I don't know.
Because it's not acceptable phase transition are the approximants.
Yes.
The measure becomes complex. Then you get roots outside the support of the measure.
Yes. Yeah. That's right. So exactly. That's the sort of thing you see in the picture. Yeah.
At the beginning, when you were motivating these explorations, you talked about certain random matrix models and how you got to play.
Or other people did. I didn't get it, but yes.
But those are very specific examples.
Yes. Yeah, that's right. Very specific boundary conditions even.
Yes.
Yeah.
Now you've moved over into the number theoretic side where you're looking at hyperelliptic curves, and then you are able to bring out like pairs and integrability. I'm wondering what this picture covers. Does it specify eventually some particular integral system, some particular Painleve equation, perhaps associated with these polynomials, or does it not?
Well, in terms of the integrable system that it covers, I mean, it's giving you solutions of the infinite Toda lattice. So that's whereas often the kind of solutions that you get in matrix models, you maybe only look on the half line with very specific initial boundary value problems. What is possible from talking with Antonio is that when you do the double scaling limit, he's been considering. I mean, I don't want to misrepresent his work, but he's been considering the double scaling limit and how you essentially get a dispersive PDE from the limit of the matrix models, and then you get some kind of it looks kind of like modulational instability or dispersive shock. So you get, if you like, the leading order nonlinear term is like the Riemann equation or Invisted-Burger's equation, which forms a shock, and in the regime, so the dispersionless equation has a shock, but the what happens is that with dispersion an oscillation develops, and the solution that you get in the oscillating region looks rather like, say, a genus 1 solution, or perhaps this kind of genus 1 solution, but then also it goes through possibly transitions to higher genus, which again could be these sequence of type of solutions. So you know, it could be that these solutions are good for telling you part of the asymptotic behavior of the dispersive shock, and then the tail or the leading edge is where you get Painleve equations. So these things are not solutions of Painleve equations because they're algebra geometric type. But in the middle, there is something that looks algebra geometric. So that should be described. That should be.
I'm just sticking to the picture you have on the board right now, which is.
Oh yeah. Yes. Yeah.
And a hyperelliptic curve.
Yeah.
Usually you get recurrence relations like the one you've written down, then there are associated equations that govern the coefficients.
Oh yes, I'm sorry, Nalini. That's a very good question, and I've been a little bit lazy, and I haven't written all those equations, but I've sort of made them implicit in my statement. But let me give you the example in genus 1, so you can actually see the equation. So
I don't want to take up everybody's time.
No. But just that this is kind of a quick thing. So in genus 1, I mentioned that it's just really becomes a symplectic map in the plane. So it's given by explicitly a formula with two parameters. So I guess what you could say is that these equations, if we eliminated V and just got an equation for D, we get an equation which looks like an autonomous limit of some of the kind of Painleve equations that you're interested in. So, for example, in genus 2, I guess you get something that would be perhaps like an autonomous limit of D. Fourth order discrete Painleve 1, yeah, something or DP2. So yeah, so if you eliminate V, you get a QRT map for D, for example. And so this is a symplectic map in the plane, and it has one Hamiltonian, one conserved quantity. And yeah, I mean, it's actually the symplectic form is really just the canonical form in these two variables that I. Or D and V, and then okay, in genus 2 you can write a nice system of 2 second-order difference equations for D and V and so on and so on. Yeah, that's right.
But my main question was,
yes,
something that has a DP1 built into it at the bottom, but do you get others? Do you get other discrete?
Okay. I'm sorry. No, as far as I know, you don't, because I mean, you only get you get one family, in each one family of maps in each genus. But so the other part, which I won't try to explain now, but if you do the same thing for odd models of hyperelliptic curves, which then you get corresponding solutions of the Volterra lattice, and then you actually do get some of the maps that you considered with Claude and Georgia and Zing. Yeah.
So that was one question.
Yes.
Okay.
Okay. Yeah.
Which is that your relationship between the hyperelliptic curve and the lattice pair at the end.
Mm-hmm.
There was a natural journey that gave you a 2x2 next. But you can also have 3x3, 4x4.
Yeah. No, that's a good point. Yeah.
And those ones would lead to hyperelliptic curves that have.
No, they wouldn't lead to hyperelliptic curves.
Why?
Yeah. So they'd be trigonal curves, or yeah. Yeah, so you would get higher degree. So in general, you would have things that are more like with different symmetry algebra. So if you had 3x3, so then you also get things like maybe skew orthogonal polynomials and multiple orthogonal polynomials. I mean, that's actually a very interesting direction, is to take it into and sort of multi-Padé approximation. So in fact, Marco Bertola has some more general results about Padet approximation on Riemann surfaces, but we haven't fully managed to translate between our two versions, because all of his things are based on starting from a measure supported on a single interval. So I'm sort of starting from a different direction and ended up with measures, on multiple contours. But anyway, I won't say any more for now. Thank you for listening. Yeah, you can. Anyone. I mean, now it's polite. Certainly, already polite to leave if you don't want to ask more questions. But yeah, please.
You were evaluated nonlinear equations coming from the Hankel determinants.
Yeah. Okay. I mean, that's a good point. So, in genus 1, I already knew a route to go from sort of a map in the plane to a map. Well, so in the end, you get you can eliminate V, but you also need to use the Hamiltonian actually in this setup. But you end up with this. So this is the second order recurrence for Dn on its own, but alpha and beta will be functions of these two parameters f and u, and also of the Hamiltonian, which I haven't written down, but it's another constant of motion. So on the orbits, on the level sets of this map, the Dn's also satisfy another recurrence. This is actually QRT type, and well, in fact, this particular type of QRT map, there's Godin's book about the beta ansatz. He actually finds this kind of recurrence for Boltzmann weights in the hard hexagon model. So he actually he finds or even the Somos relation. So so then the point is that you take Dn is given by this ratio of Hankel, and you get this bilinear equation. Okay, so there are general things about theta functions. So I mean, as I alluded to, you can give solutions for these Somos in theta functions, and in the higher genus case also you can write down a formula where these Hankel determinants are also given by some theta function formulae, but in dimension G. And then there are results about the space of the dimension of spaces of theta functions of a particular weight, which then say that if you take quadratic products of deltas of these Hankels, then they must, because they're given by theta functions, they must satisfy some quadratic relations of some order. Although the order actually grows kind of exponentially with the genus, so it grows more like 2 to the power of g. So in genus 2, generically, the relation you get is it's a Somos 8, in fact, and it's already outside the cluster type or the BKP type. It has too many terms, so so you can write down. So this is what you can do. So certainly in genus 2, I've written down explicitly what the relation, the nonlinear relation for the Hankel determinants. It's a bilinear equation of order 8 that's satisfied. But in general, as I said, the degree of the order of this relation grows something like 2 to the g. So it gets rather complicated. So it's possible that you could take some other determinants, combinations of determinants, which would satisfy lower order or lower degree, but I don't know how to do that in general. So I know that there are bilinear relations, but the order grows rather. So in fact, this is what got van der Poorten stuck on this problem. His view was he was trying to generalize this Somos 4 to beyond elliptic, and he knew about Somos 6, which is quite a beautiful relation, which has 4 terms in total, and it also has the Laurent property, and it's very nice. And he wanted to find that in genus 2, and he found that in this construction he could not get the general Somos 6. He could put some constraints on the parameters on the curve in a certain way, and he could get a sort of special case of SOMA 6, but in general, he couldn't see what he would get. And the reason he couldn't is because in general, it's a SOMA 8 and it's much more messy. But I mean, I originally did it with computer algebra, and it took quite a few tricks to actually, and even to write down the formula is, I mean, to write down the coefficients is huge. I mean, it's horrible, in fact. Yeah, so that's kind of. But I mean, there are many other integrable systems. As I said, like reductions of discrete KP or reductions of BKP, where you really get nice bilinear sort of Poisson type relations, which are of manageable size, and also maybe coupled Poisson equations as well, which are manageable. But if you just take a single Hankel determinant, then it rapidly, the complexity explodes. So yeah.
So in this particular solution you construct,
Yeah.
you have maybe you said it, I missed it, the analog of a string equation or a resurgent constraint.
Yeah, well, that's what I was saying is that I mean, you see the case that's in your paper that's like also in Katz van Merwicke kind of stuff, and is and Dijft and other people, and even the quantum gravity. Well, I mean, the quantum gravity literature, which I read a long time ago, they sort of more or less go to the continuum limit immediately and focus on that, and they sort of didn't focus so much on the discrete equations originally. Before, you know, then other people understood that there's already all this structure on the discrete level as well. So if you set V to be 0, then you just get a single string-like equation for D. And so this equation, for example, if I put the dn squared over there, is something like a sort of, this is like a dp1 actually. This, if you had some dependence on n as well, then this would, I mean, there is a qp1 equation, which is not an ordinary difference, but well, maybe there is. Yeah, I think you can have a Q type or yeah. So yeah, so exactly. So yeah, this is sort of like an autonomous version of a string equation for D. But I don't know so much about coupled string equations. But I mean, in general, you know, if you have this commutator of operators, you have a choice whether you write it as a system or you write it as a single large order difference equation. And in a sense, it's more natural to write it as a system. But it's just it just happens to be nice that here, if you isolate these two variables, which are the recurrence coefficients, then you can get some nice systems. I mean, I did write out the, if you want to see it, but again, I don't want to bore people who are not massively interested in string equations, but the system in genus 2 is quite nice. Let's see real equations. So in fact, I mean, also in fact, the Poisson algebra you get in this is quite nice. So you get an analog of what are called Mumford systems. So some algebraically integrable systems which Mumford consider which come from the stationary flows of KdV. But here they're like with even order spectral curves. So there are also even order Mumford systems. And then one of my current collaborators, Paul Vanhaecke, is an expert on algebraic integrability. And he's looked at actually constructing. So in fact, what you find from this construction or the other construction we have with Stilcher's fractions, you don't get the canonical Mumford systems, but in one of the cases he shows that it's the Poisson variety is isomorphic to the one that you get from Mumford systems. So yeah, these are there. So the point is that there's actually with these 2x2 Lax matrices, they define very nice Poisson varieties, and what happened in this case is that I worked out this system in genus 2. So this is a two coupled second order difference equation. So overall it's dimension 4. And then I managed to spot that the symplectic form is like this, that there were invariant symplectic form. And then I worked out the corresponding Poisson brackets, of just the inverse of the symplectic form, obviously the Poisson tensor. And actually it gives you a very nice Poisson algebra for these matrices, this space of two dimensions. So you basically really like formulas. I love formulas, but not everybody loves formulas. Then there's a kind of there's a natural sort of gauge choice, so you can't really see so well here, but this is basically a Lax matrix, which is P minus P, and then this is Q, and there's R. In fact, but you really need to do a gauge. So I said that the coefficient in front of Q called UN is a really kind of annoying gauge factor. You get rid of the gauge factor, and then P and R are monic polynomials of degree G plus 1 degree G. G is a non-monic polynomial of degree G, and so overall you get a phase space of dimension 3G plus 2, and then you can actually work out the Poisson brackets of the entries of this matrix, and they give you very sort of symmetrical formula. So what I did was I worked it out found this thing in genus 2 that I just showed you, and then I worked out what it did on the Lax matrix, and then I was able to prove that this Poisson algebra works for any G. So you have a nice Poisson algebra, and then it's easy you can actually prove directly that the coefficients of the spectral curve commute with one another, just straight from this algebra, just pure algebra at the end of the day. And then, yeah. Yeah, but I don't know an R matrix for this. Let's see how the matrix is R. Thanks, Andy. Again.